So this is 2 talks for the price of 1. So 2 different topics. So the reason I wanted to do that was because I wanted to show you something I was doing while I was actually working at the Newton Institute in January and February, where I contributed to the recycling efforts of the Institute by hundreds of pages of wasted calculations. So, okay, anyway, so this is the first part. So I explain the problem and then I talk about who worked on it. So this concerns the Onsager functional with the Maier-Saupe molecular interaction, which is given here in terms of the probability density function rho of molecular orientations. This is for a homogeneous nematic. S2 is the unit sphere. Here we've got an entropy term I've divided by the factor here and put it all into this constant here. So there's usually be a Boltzmann constant here, for example. And so this is the entropy, and this is the interaction term, which is minus some constant kappa over 2 times the Euclidean norm of the second moment tensor of the probability density function u. So sometimes you would put the q tensor here, but it doesn't make any difference. Okay, so that's the functional, and so as we know, M is a symmetric positive matrix with trace being 1. Now the critical points correspond to what we in fact let's get back a moment. So there's the functional. So I want to calculate the critical point of this. So I'm going to take the derivative with respect to rho. Of course, the integral of rho is 1, so we have to take care of that. Anyway, we get 1 plus log rho is kappa m of rho dot p tensor p plus a constant. That's the Lagrange multiplier corresponding to the fact that the integral of rho is 1. And so we see that rho is given by this exponential, kappa times this, divided by its integral to normalize it. But the problem is, of course, that m depends on rho. So this is a matrix, but somehow we have to show the consistency here. I just wanted to make a remark that this implicitly assumes that the infimum of rho over the sphere is strictly positive. So in work with Apollo Majumdar, in sort of essentially the same problem, we struggled to show that the minimizers satisfy rho strictly is bounded away from 0. I mean, the issue is that rho log rho is singular at rho equals 0, so you have to be a little bit careful. It's not that difficult, but anyway, you have to do something, and it really is an issue because in related models there are a rho that actually have compact support on the sphere. So perhaps one should be sort of saying what we mean by a critical point, allowing for rho to be 0 somewhere, some kind of variational inequality. But anyway, that's not done. Okay, so let's write rho in its eigen function expansion. So I'll take EI to be the usual Cartesian unit vectors. So of course the trace of rho is 1, so the sum of lambda I is 1. And so therefore we have to solve these equations. These are the equations we have to solve. So the integral of pi squared times this exponential is lambda I z. Z is this, for I equals 1, 2, and 3. Okay, so
you are assuming M to be symmetric?
M is symmetric. M is the second moment. It's the integral of p tensor p against rho, so it's automatically symmetric. Okay, so there's the equations. Again, I just call them Euler-Lagrange for short. And now in some, what I think could be said to be classic papers now, Fatkullin, Slastikov, and Liu, Zhang, and Zhang essentially independently characterized all solutions, and in particular showed that they're axisymmetric. Okay, that means that there are no solutions with the lambda I all different. Okay, and there's also another proof came a little bit afterwards where they claim to find a a somewhat simpler problem, a somewhat simpler proof of the fact that these solutions are axisymmetric. This is the most difficult part of these papers, to show axial symmetry. And you know, I take my hat off to Larry and others who did this. Is not trivial at all. But anyway, all these proofs were too complicated for me to understand, so I wanted to find a proof which was simple enough so that I could understand it. So now, in a somewhat similar problem from elasticity, there are solutions with the lambda I distinct, and they come from secondary bifurcations of branches which are axisymmetric, where two lambda i's are equal. So you've really got to use something special about this form in order to prove that the lambda I can't all be different. So anyway, here's my proof. And okay, so it's based on this lemma. So this is just an integral identity for functions on the sphere. Okay, I've written it down for lambda 1 and lambda 3, but you can permute things to get different versions. Okay, so now, why is this true? Well, it just comes from applying the divergence theorem on the ball. So you take the unit ball, and here's this U here is, as you can check, is a divergence-free vector field. Okay, so here we're taking P, of course, to be in R3. Okay, but it's divergence-free, and so therefore, by the divergence theorem, the integral of U dot P over the sphere is 0. Okay, and if you calculate that integral, you find you get exactly this. Okay. So once you've got this, then you see that we're told what the integral of P1 squared times this exponential is. It's lambda 1 times z, and the integral of P3 squared times this exponential is lambda 3 times z. So we're going to get a lambda 1 minus lambda 3 here, which we'll be able to cancel, right? So suppose all the lambda I are distinct, then we get from the lemma that 2 kappa times this integral is z. Okay, so now we can change 3 to 2, we get the same thing, and subtract. And so we get the integral of P1 squared times P3 squared minus P2 squared times the exponential is 0. But here you can swap 2 and 3, integrating over the sphere, because swapping 2 and 3, I mean, that's the area element on the sphere is invariant to doing that. So therefore, we also have that this is true. And we add them together, okay, and we get that this integral is 0, where g is the difference between these two exponentials. And now we see the exponential is a monotone function, so this is positive provided this is bigger than this, which is exactly that kappa lambda 2 minus lambda 3 times P2 squared minus P3 squared is positive. So you see that, in fact, since I've got a P3 squared minus P2 squared here, the integrand has one sign, and it's not identically 0. That's a contradiction. So that's the proof of radial symmetry. If there's an idea to this, it is that in all the other proofs, use is made of polar coordinates. Okay, and polar coordinates means you fix some axis for the polar coordinates, and that somehow is awkward when you want to prove symmetry, because somehow it desymmetrizes the problem. So this argument, in some sense, works with Cartesian coordinates, and somehow you're not faced with that particular issue. Okay, that was the first talk. Okay, this is the second talk, completely different. This is joint work with my last Oxford PhD student, Lu Liu, who just graduated. He's not staying in the academic world. He's evading Trump's oil sanctions by moving oil around, from different places. Anyway, this is his thesis. So it concerns exterior problems for the two-dimensional, one-constant Oseen-Frank theory. So here's the Oseen-Frank theory that we'll be familiar with. It has a free energy I that depends on the director, and through this integrating this quadratic function of the gradient with some n's floating around, the ki's are the Frank constants, n belongs to the unit sphere. Now in the two-dimensional case, we have n of x is n1 of x1 and x2 and n2 of x1 and x2 0. And then curl n is this expression, n dot curl n is 0, n cross curl n is curl n squared, which is this, and the saddle-splay term here is 0. Now I want to talk about an exterior problem. So I suppose we're working in RD, d equals 2 or 3. Ideally it would be 3, of course. We have a finite number of objects, and we're going to work exterior to these objects. So these are going to be bounded open regions with sufficiently smooth boundaries, disjoint. And we're going to work in RD minus the union of their closures, and we're going to specify what n is on each of the boundaries of these objects. And the question is, what can we say about equilibrium configurations n that satisfy those boundary conditions? And in particular, what can we say about their behavior at infinity? So it would be very nice to be able to handle the case at d equals 3 for general elastic constants, and then to allow these objects to move. But I'm afraid that we are unable to do any of these things really. So first of all, we're going to assume that the omega I are fixed and that we're in 2 dimensions. And then, unfortunately, we're going to work in the one constant case. So k1 equals k2 equals k3 equals 2, and k4 is 0. Now, why is the one constant d equals 2 case so much simpler than everything else? Well, firstly, you can identify R2 with a complex plane. Okay, you can write z is x1 plus I x2. And then you can identify n with the complex field n1 of x1 x2 plus I n2 of x1 x2, which we can use formally write, because n is a unit vector, as e to the I phi of x. Now, the Euler-Lagrange equation for this one constant energy is the harmonic map equation, Laplacian n plus the gradient of n squared. N is 0. And in terms of phi, you find that, so I was calling, let's get back here. I was calling this n tilde, the complex n, the complexified n I call n tilde. Okay, so now that turns out to be I e to the I phi times Laplacian. Phi is 0. So this is equivalent, at least locally, to the linear Laplace equation that the Laplace of phi is 0. So in particular, since solutions to the Laplace equation are smooth, equilibrium solutions of locally finite energy in the 2-dimensional one constant case are smooth, and there are no defects. Now here's an interesting thing. This is simple. Now suppose you take 2 equilibrium solutions, n tilde of z and m tilde of z. Then we can multiply them together as complex numbers, right? And that will give another solution, because when you multiply e to the I phi by e to the I psi, you get e to the I phi plus psi. And so if phi and psi are harmonic, so is phi plus psi, right? And similarly, if you invert the complex number 1 over n tilde, that's also an equilibrium solution. Okay. So one interesting consequence of that is that any constant rotation or a rotation plus reflection of an equilibrium is also an equilibrium. So if we had, for example, this situation, some equilibrium solution which satisfied these boundary conditions, then we just rotate it through an angle, pi, and then the boundary conditions change to this, and you just rotate whatever the field is here, and you get an equilibrium solution for this. Okay? So that's kind of interesting. That's not the case for general elastic constants. It's not true. Okay, so, but it is true in this 2D1 constant case. Now, in polar coordinates, r theta, Laplace's equation can be written as Laplace's equation with respect to the logarithm of the radius and the angle theta. And one solution is phi is equal to theta, which gives the two-dimensional hedgehog e to the I theta is z over mod z, which has finite energy only for bounded domains that don't contain the origin, because we're in 2D. So now this solution, while it solves Laplace's equation locally, is not a globally defined smooth solution in terms of theta because of the jump of 2 pi in theta as you circle the origin. So it's a question about how this can be remedied. And so let me just remind you first of all of the definition of the degree of a curve. So if you smoothly parameterize one of these boundaries d omega I by t going from 0 to 2 pi, then you can write ni of t as cos phi of t sine phi of t with phi smooth, and you define the degree of ni then to be the integral of phi prime, or the average of phi prime. So it's 1 over 2 pi times phi at 2 pi minus phi at 0. And so here are some examples of degree 0, degree 1, degree 2 vector fields. Now here's a very interesting trick due to Carbu, which greatly simplifies the analysis of this problem. So pick a point AI in the interior of each of these regions omega I. So for convenience, you can choose the first one 0 to be the origin of polar coordinates, and let di be the degree of ni. Then you can write any equilibrium solution as n tilde of z is z minus ai over its absolute value to the power d is z minus a1 over mod z minus a1 to the power d1 up to z minus am over z, the absolute value of z minus am to the power dm e to the I phi of z, and now phi is a smooth solution of Laplace's equation in the whole of the exterior region. So in other words, these sort of putting these kind of hedgehogs in to the right degree somehow unwinds things in such a way that the phi now is a smooth harmonic map in the whole exterior region. And roughly the rough proof of this is that you use these properties of multiplying equilibrium solutions together. So z minus ai over mod z minus a1 mod z minus a1 is an equilibrium solution. So that raised to the power minus d1 is also an equilibrium solution. So that times this is a equilibrium solution, and so this is an equilibrium solution. And you check that this has degree 0. And since it has degree 0 in the exterior domain, that means you can globally solve for phi. Okay. So now we're going to let BR be the ball center 0 radius r. So remember, 0 is inside one of these regions, inside omega 1. And so since all the regions are bounded, they'll all be included in B of R0 for some large enough R0. And I'm going to choose as a set of admissible director fields X, which are unit vector fields. This should be S1. There's too many misprints here. N taking omega to S1, the circle, because we're in 2D, so such that the energy on any finite part of the exterior region is finite. Okay. Now, of course, you can't expect the energy, you can't expect the total energy to be finite because we're in 2D. So this will in general not happen. Okay, and also satisfying the boundary data. We let k be the sum of the degrees. And now we have a problem in that there are topologically distinct possible equilibria. So you can split X into countably many homotopic classes, which are topologically distinct families of n, so that director fields in two different homotopic classes can't be continuously deformed one to the other. And now using this Carbu representation, you can identify the different homotopic classes to adding different multiples of 2 pi to the boundary values of phi on each boundary d omega I. So that's you can show that characterizes all the different homotopic classes. And so here's the result. So so let k be the sum of the degrees. And now what we do in order to fix the fact that the energies are typically infinite in the exterior domain is we renormalize the energy. We subtract off minus the k squared, that's the total degree, over norm x squared. And in each homotopic class, there is a unique minimizer of this functional. It's a smooth harmonic map, and at infinity it tends with this estimate to this particular form, so cos k theta plus beta c sine k theta plus beta c. Beta c is a constant which is determined by which is unique, and it's uniquely determined by the homotopy class. And in each homotopy class, there's also a harmonic map with this energy being infinite. Okay, so in some sense we're picking out good solutions that don't grow too fast at infinity. And furthermore, this energy attains a minimum in X, that is in the union of all the... Hi, yes, you're asking a question.
Can I just ask a very quick clarifying question? So this beta C, you have it as a real number. Is it really a real number, or is it mod 2 pi?
It's a real number. It's real. Okay, so now also E depends on... well, okay, I see what you see. So you're saying
if it appears in sine and cosine.
Yeah, it's inside. You're absolutely right. Yes. So it's unique up to multiples of 2 pi. Correct. It's unique up to multiples of 2 pi. Absolutely right. Thank you. And okay. And so now, if we now minimize on the whole of X, that's on the union of all these homotopy classes, that also attains a minimum, but in general it's not unique. Okay, so and here's a counterexample for uniqueness of the minimum in X. So here we have two circles with hedgehog boundary conditions, and so there is a minimizer, and it's smooth. So what is its value what is its value halfway between the spheres? It's got to be pointing in some direction, right? So maybe it points like this, but then when you reflect it, you will get another solution, right? So whatever it is, you can always reflect it to get another solution. Now you might think that this is something to do with orientability. Now in fact you can handle the case of line fields, i.e. non-orientable director fields, by the trick of squaring n, okay? And that turns the problem, the non-orientable case, into the orientable case. And then you can apply this counterexample. So it's actually, you still get non-uniqueness even in the non-orientable case. And now, in the 2D case, there are two elastic constants in general. We consider the one constant case. The two constant case is still really much more difficult than this case I've described here, and in particular, there can be radial solutions that are periodic in the logarithm of r. So that's very different from the situation we have here, where we have some approach to a particular solution as r goes to infinity. And I think that's everything here. That's everything.
So are you excluding half integral defects in what you
they have infinite energy, of course, in the 2D
well,
theory.
but if you have a boundary condition that it
Oh no, well half integral. Well, that would be the non-orientable case. That's the non-orientable. So you can do that by reducing it to the orientable case by squaring the vector field.
and ultimately this is no different from asking what happens in superfluid helium.
I have no idea. But if you say so, I'm happy, of course.
Squared, you have similarities.
You have a question there?
Two related comments. So, one problem that has very much this flavor, but I must say probably the mathematics are very different. Assume that the omegas, instead of being fixed domains, are actually the isotropic phase of the liquid crystal. In which case, it means that these omegas are free domains, so you have free boundary problems with surface energy. So this is a very interesting case, I think, because it corresponds to the tactoids in harmonic liquid crystals. And there is relatively little work done. These domains have singularities because we make these kinds of casts, which are a signature of these tactoids. So, of course, the proof would be very different, but definitely it is within this point of view. And then the second, and this is perhaps more unrelated, so suppose that, again, that the omegas are free boundaries, right? But you fix the curvature of these boundaries, okay? So one case is, suppose that the curvature is constant, and then probably, and that I'm guessing with standard results, there's problems where I think in the parametric case were basically settled by Lyons in the 90s, and Lyons and somebody in his group, perhaps Coron. But suppose that now you give a little perturbation to this constant curvature and you introduce some heterogeneity. So then you get a very nice problem where the minimizer is not achieved. And for kind of more generic energy, is you probably know this work, but it's some work by Maiji and another co-author, where they exactly show that there is no minimizer for this kind of problem. So it's actually probably maybe apples and oranges, but they are very, your problems are very suggestive of the situation.
Well, thank you for these suggestions. Perhaps the next simplest thing to do on this problem is to calculate the forces on each omega I, the total forces, because that you could make into some kind of poor man's dynamic theory, probably, in 2D. Okay.
We're perfectly on time, so let's thank Zhang again.